In this program we find out what David does not know about magnetism. We see how a house is wired. And we poke around the Jumbotron. I am a Armatron. Short and stout. Here is my hand. Here is my snout. Hee 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 hee.
There are three important things that you should know if you plan to work on your house wiring. 1, don't get zapped. 2, don't burn the house down. And 3, know what you do with. It's not normally the policy of Acme to encourage people to do things that they really shouldn't be doing. But there are too many people willing to jump right in with no knowledge of how the system works or the implications of a sloppy job. So, number 1. The electric potential of ordinary house current is enough to seriously hurt or kill you. If you don't know how to safely disable a circuit, don't work on it. Number 2. All things that conduct electrical current have a property called resistance. Current flowing across a resistance causes heat to be generated. That was a scale model demonstration. The wire I just burned was copper wire with 10 amperes of current flowing. Currents in the house circuits go as high as 40 or 50 amps. The wires are larger and have less resistance, but this should point out the need to use the correct gauge wire in a circuit. This also demonstrates what the fuses or circuit breakers are for. Resistance isn't just a factor in wire heating. Every connection in the system can be a sore point. A loose connection can develop resistance in several different ways. No matter how the connection develops resistance, it results in heat. For this reason, all connections of any type have to be in metal or approved plastic boxes. Number 3, here's how it works. The electrical energy comes into your house as 240 volts. If you're older, you say 220 volts, but the voltage is sort of nominal anyway, so call it whatever you want. The actual voltage varies from place to place and time to time. The 240 volts comes to your street is about 5,000 volts. A transformer on one of the poles serves you and your neighbors with your 240. So by now there are a lot of people hopping up and down shouting at me, "Doesn't this idiot know that we have 120 volts in North America, not 240? That's what it says on my toaster." Well, I'm just not being just continental with my 240 volt figure. The transformer that supplies your house supplies 240 volts to it, but the transformer winding is tapped in the middle. The tap on the transformer is also fed to your house, and the tap is spiked into the earth as well, neatly dividing the 240 volts in half. This explains why 3 wires come into your house. The grounding of the center tap is necessary for all sorts of reasons, from lightning protection to people protection. If no part of the system was attached to ground at any point, little leakages here and there would have us all dancing in the street. The grounding at the house is usually done to a metal water pipe entering your house from the water main. Don't ever fool with this. If you lift your ground, all of the metal parts of the electrical system will assume an unknown potential with respect to the damp basement floor and the kitchen sink. So, we have 240 volts split and grounded in the center. The white wire entering the box is the center tap. Its official name is neutral. The black and red wires are the 2 ends of the transformer winding. Sometimes these wires are black and black. Red and black are interchangeable in house wiring, so we have to refer to them as the hot legs of the circuit. Between them is a potential of 240 volts. From either hot leg to the white is 120 volts. All of the metal parts of the system are connected together by bare copper ground wires. At the entrance panel, neutral and ground are connected together. Most of the circuits in a house are connected from neutral to one side of the service, red or black, and operate on 120 volts. Neutral and ground are at the same electrical potential, but neutral can be used to carry current. Ground never does. It's there for safety. Branch circuits are protected by 15 amp fuses or circuit breakers. Many lights and or outlets can be daisy chained to one branch as long as you don't expect to draw more than 15 amps total. Usually the local electrical codes will limit the number of outlets on one branch to 8 or so, but it's silly and inconvenient to share that many anyway. There are 20 amp branch circuits too, but they need a larger gauge wire. Heavy duty loads like electric stoves and clothes dryers are connected across the entire winding of the transformer. And they work on 240 volts. But even though these are 240 volt appliances, the neutral is still important to them. The lights in the stove and the motor in the dryer work on 120 volts, so they're connected between the neutral and one of the hot legs. The circuit breakers for these are doubles, one on each leg. The handles are connected together so that if one leg blows, the other one's shut off as well. Nowadays, kitchens have to have these. It's a split receptacle. The neutral is wired conventionally, but each half, the outlet, is fed from its own branch. This allows the wanton connection of heavy loads like toasters, coffee pots, and things like that. The tab that ordinarily connects the two hot sides is broken away, and the split halves each have their own wire to their own breaker. This raises an interesting question. If one side has a toaster connected and the other's empty, the 10 amps to the toaster is flowing in both the hot and the neutral. If an identical load uses 10 amps from the other side, is there now 20 amps flowing in the common neutral? Nope, not if it's wired right. Split receptacles sharing a common neutral have to be connected to different legs of the service. With two identical loads connected to the outlet, no current will flow in the neutral. Both loads are actually connected in series across the 240 volt supply. The neutral in a split outlet only ever has to carry the difference between the two sides, which will never be more than 15 amps in this example. The rules and regulations of local electrical codes were created to standardize electrical installations in any given area, but they also ensure that no potentially dangerous situations can occur in a seemingly safe layout. The case of a split receptacle accidentally connected to two fuses or breakers that are on the same side of the transformer is a great example. It would apparently function normally, but the neutral wire can be forced to carry twice its rated current. Fooling with house wiring can be dangerous for all sorts of reasons, so when Uncle Clem or the neighbor drops in to do a little weekend work for you, ask him a few simple questions, about grounding and the 120, 240 volt thing. If they can't answer those questions to your satisfaction, well,
popcorn. Yum. Yum. How do I put this in my mouth? My arm does not reach my mouth. This is stupid.
this is what 402 square yards of video looks like. About the size and shape of an average residential building lot. It's the Sony Jumbotron at Toronto's Skydome. How much does it cost? Well, you and I aren't likely to have one in our house soon. For one thing, it comes with its own studio. This is the Jumbotron's control room. During events at the Skydome, 5 cameras cover the action for the sole purpose of keeping interesting pictures flowing. As well as the cameras, there's an electronic file of still pictures on hand. Using standard video production machinery, stills of logos can be captured with a small color camera, and titles can be composed for direct display or superimposition. The most important accessory for the Jumbotron is this machine. It can stretch, squeeze, and reposition pictures in real time. Big as it is, the Jumbotron only displays the center 1/3 of its video input. Live pictures from the cameras are framed with the Jumbo's display area in mind. Logos can be shrunk to 1/3 size to fit with a half-size crop picture, or 3 normal video frames can be shrunk and displayed side by side. A safe area generator in the control room generates white reference marks on the control room monitors to guide the positioning of the pictures before they're sent to Jumbo. This is how you turn on the Jumbotron. This is the Jumbotron's power-up sequence. It's performing some self-tests. The picture on the Jumbotron is made up of 67,200 of these. This is a Trini light. Each Trini light displays 2 pixels of the total picture. Pixel is short for picture element, the smallest point of light in the picture. Trini lights work on the cathode ray glowing phosphor principle, similar to your color TV. The 3 stripes on each half show the location of the red, green, and blue phosphors. The chicken wire mesh over the front helps drain away static electricity so that the Jumbotron won't attract dust and grease like a home TV does. The back of the Jumbotron is about what you'd expect, only bigger. The 67,000 Trini lights are assembled into units that contain 16 Trini lights each. That's 32 pixels if you're still counting. 5 floors of catwalks provide access for servicing. 5 floors is big enough, but remember, the Jumbotron's 3 times wider than it is high. There must be a better phrase than real big, but it's the only one that comes to mind when you stand at the back. This is one of 27 cooling fans. In case you feel intimidated by your own TV set, you'll be pleased to know that each unit has a familiar sticker on the back. Refer servicing to qualified personnel. Geez, I hope they don't have to take it back to the shop. The folks at the Dome were very nice about letting Acme play with the Jumbotron for a couple of hours. Given the huge scale of the Skydome itself, a little nonchalance towards a 1/12 of an acre TV picture is natural. But for a kid who grew up with a 14-inch black and white set, well, let's just hold a bit. There. And my gym teacher said I'd never make it to the stadium. Magnetism is one of the oldest studied phenomena on Earth, and these days our lives run on magnetism. You'd think we'd know more about it. An ampere is a unit of electricity, a liter is a unit of liquid, an inch is a unit of measurement, and a second is a unit of time. Can anybody give me a unit of magnetism?
Nope.
Right. Well, there's Gauss, which my encyclopedia pronounces Gauss, and Oersteds, or Oersteds, Teslas and Webers, named after a mathematician, a natural philosopher, an electrician inventor, and a physicist. Magnetism seems to touch all areas of scientific thought. Exactly what is a Gauss, Oersted, Tesla, and Weber escapes the Acme School of Stuff. In all of the reference work, the units are defined in terms of each other. Some things we do know. A magnet is a thing in which a high concentration of magnetic lines of force pass through its body due to the alignment of its constituent atomic dipoles. What this means is that you can consider a magnet to be made of zillions of tiny magnets, all aligned in the same direction. This theory is backed up by the fact that no matter how many little pieces you cut a magnet into, they'll all have a north and a south pole. When the tiny magnets are all arranged at random, the magnet is demagnetized. This is a clue to how information is left behind on your average magnetic material. The lines of magnetic force exist largely between the magnet's poles. In the case of this bar magnet, that's something like this. The lines of force form a closed circuit. Quantifying the strength of magnetic fields ought to be simple, but it isn't. A little rooting through a surplus store came up with this Gauss meter. Acme shops for all of its sophisticated precision measurement devices at the surplus store. Now this one came with no instructions, and we're not too sure what a darn Gauss is, but its operation was carefully checked against my Boy Scout compass, and it seems to be working all right. According to this meter, the Earth's magnetic field seems to be about 1 Gauss. The problems with measuring magnetic intensity are twofold. For one thing, I have to make the presumption that it's measured at the peak of those magnetic lines of force. For another, it follows the inverse square law. That means that its intensity falls away as the square of its distance. One way to get a picture of the inverse square law in your mind is to imagine spreading a fixed amount of peanut butter over an expanding sphere. A sphere's area varies proportionately with the square of its radius. That means that when the sphere is twice as big, there'll be 4 times less peanut butter at any one spot. Magnetism follows the same laws as peanut butter. So, how to use this to measure intensity? I decided to sort all of my magnets by measuring Gauss at the strongest part of the field. Magnetizing something seems to be a matter of aligning those constituent atomic dipoles. The effect seems to be instantaneous and depend on the strength of the applied field. Information is written to magnetic media using electromagnets something like this. They're called heads. The magnetic force is concentrated in the gap between the 2 poles. The intensity and polarity of the magnetism is proportional to the applied electric current. The passing material forms a closed magnetic circuit in the gap with those lines of force, and it receives patterns of magnetism that correspond to the way the current was varying. The amount of magnetism left on a tape or disc depends on the characteristics of the medium. Now, I have a list from a manufacturer that shows the ability to be magnetized of various media. The units aren't mentioned, but I think they should be in Orsteds. But no matter what the units really are, the numbers will give you a relative feel. They go like this. Double density diskette, 300. Normal audio cassette, 365. High density diskette, 600 to 700. Videotape, 700. And chrome audio cassette, 1100. Now, this means that ordinary audio cassettes and computer discs are the most easily written of magnetic media. It also means they're the most easily rewritten of magnetic media. Just to see how easily a disc could be damaged, I set up a test. I made a disc with 10 short files on it. And between each of the short files, I copied a fairly long file. That was to ensure that my 10 short files were scattered all over the disc. A batch file called Go finds and displays all of those 10 short files when I type the name of it. Ten copies of that disk were subjected to various magnetic tortures in the Acme lab. Now, even though these are the cheapest discs obtainable, they showed a remarkable tolerance to torture. This disc got one quick broadside hit of the 1000 Gauss ceramic magnet. Only one file was damaged. To be fair, if the one damaged file had been the disk's directory, it would have disabled the entire file structure. This survived the 400 Gauss speaker thus, but a second application thus killed it. This one survived the fridge magnet. Just to test the contact time theory, this one spent the night under the fridge magnet. No damage. This paperclip dispenser magnet measured in at around 300 Gauss. I couldn't hurt the disc with it at all. This was probably due to this tiny plastic ridge and the inverse square law. Now, I thought for sure that this was going to be trouble, especially since the magnetic field from the motor caused the computer monitor to bend. It was okay. I repeated the torture 10 times. It was still readable. This one died in an eel attack. One brief contact with the eel skin wallet and poof. A year or so ago, there were a lot of reports that eel skin wallets were erasing the magnetic strips on credit cards. All of the media reported on it. Our national broadcasting service propagated this information at least 3 times when I just happened to be listening. One of the reports was from a so-called informed listener who phoned in to share the fact that eel skin wallets were made from the skins of electric eels, and that's why they damage magnetic stripes. This kind of totally unsupported reporting of science really ticks off Acme. So listen here, you reporters. In the first place, according to the dictionary, an electric eel isn't even an eel. It's a fish. In the second place, according to the manufacturers of these wallets, they don't use electric eel or fish skins. The clue to all of this eel bashing sits right out front. The closure. It is magnetic, and its field weighs in at a hefty 1,000 Gauss. One touch was enough to damage the test disc. Later, eel skin products dropped the magnetic catch in favor of a more credit card friendly latch. Now, Acme doesn't want to suggest that you get cavalier with your discs and tapes. Keeping them away from magnets of all kinds is a good idea. Just don't be too quick to repeat stories that you hear about someone whose entire video collection was ruined by the airport radar 1 mile away. If powerful magnets could project as far as most people will tell you, the Boy Scouts would all be lost in the woods. And if an eel wants to borrow your credit card, you have nothing to worry about.